Alright, hey everybody. We're going to continue talking about resistors and actually introduce circuits that have both resistors and capacitors in it today. So it's going to be an interesting one. Um, and you may find it helpful for the homework as well. So stay tuned if you're struggling with some of the homework problems. Last lecture we introduced the idea of current and resistance, and we talked about the resistance addition rules that probably a lot of you are familiar with already, but that's fine. And then we did some example problems, and one of the things that I love to do on midterms and finals, etc., is to take a circuit and then short circuit it. So that's making an electrical connection from one end of the circuit to another part of the circuit that's sort of not supposed to be there, and then show ultimately that that tends to increase currents, things like that. You know, I haven't dealt with this for too much. I used to have a car that would have blown fuses from time to time. And so whenever some piece of metal touches some other piece of metal that's not supposed to touch, often that can decrease the equivalent resistance and cause a spike in the current, which causes a spike in the power, which causes things to get heated, to get hot. Hot things sometimes melt, and that's why we have fuses, is to prevent that from happening. Anyway, okay, so there's a couple different ways of thinking about circuits. And so this is all relevant to, I believe, homework 6, although it could be relevant to other homeworks as well. And so let's talk about that. So there's one method of figuring out, say, for example, the current coming out of this battery would be the equivalent resistance method. And so you take all these resistors and you say, okay, well, let's find the equivalent resistance. We'll notice that these two are in parallel, so we can combine those. And then once we combine these, then we're left with a series circuit, right? And so we can come up with an equivalent resistance that looks like this, and then use that to figure out how much current is coming out of the battery. So that's sort of the first way of looking at this circuit, which is fine. The second way I can only characterize as the Chris Orban way, which is that you look at these resistors, which are in parallel. Because they are in parallel, you know the voltage drop across this is the same as the voltage drop across that. By the way, the Chris Orban way I would characterize as just writing down as many equations about the system as you can, and then just sort of seeing what you can do with it. And so one of the equations that you know is that these voltages should be the same. You also know that the voltage drop across this thing plus the voltage drop across these things plus the voltage drop across that thing should add up to the voltage of the battery. Now notice that I don't have V3 here, right, delta V3, because these are wired up in parallel. And so once you've hopped from this part to that part, you're already sort of over this resistor. So that's why you only need the delta V2 there. So this is just kind of the way that I'm thinking about it. Now, last time from last lecture we learned that the voltage drop is the current times the resistance. And so we know that this is true. So the voltage drop across this resistor is going to be the current through this resistor times the resistance. Same thing for this one, same thing for this one. And then hopefully you appreciate that the current through resistor 1 and the current through resistor 4 had better be the same as the current coming out of the battery, because there's no other place for the current to go. If it did go out somewhere else, then things would start charging up, and then weird stuff would happen. So, so this is true, and then one more part of the way that I think about these problems is that we have these junctions here. So there's a junction here where the current from R2 and R3 sort of combine. The current from R1 splits into two. And the thing you have to remember about these junctions is that you'll never have a situation where this happens. So if the current really was going in all three of these directions, that you remember the electrons go the opposite direction of the current, so that would imply that the center of this thing gets more and more and more and more positively charged. And eventually it would be so positively charged the thing would just explode. What really happens is that this thing, if this were to happen, this thing would get positively charged, and then one of the currents would flip, because once with enough positive charge, the electrons start flowing backwards, but back to where the positive charge is. So this never happens. The only exception is in the movies with the flux capacitor from Back to the Future. Anyway, so I think I said all these things. So this never happens. What does happen are the things more like this. You have the current, and the current splits into two, and so you can say there's current I1 is equal to I2 plus I3. But one of these could be negative. So if you're doing an equation like this, you find this is negative. If this is negative, that just means that this is happening. These two currents are combining to go into current 3. So if you find a negative current, don't be alarmed. That just means that the current is going in a different direction than you thought it was. So I would use something like this. I'd say, okay, well, in addition to these equations, we also know this equation. And then I would say, all right, I've got a system of equations here. I can try to solve this system of equations, and ultimately try to find I1 and I4, which should be the same as the current of the battery. And that's how I would, as an idiosyncratic, somewhat socially awkward, but not completely socially awkward physicist, would go about this problem. Okay. The third way is using what's called Kirchoff's loops. Now, the Kirchoff's loops, you still need to have the current rules, so we still need to be able to come to this conclusion. The Kirchoff's loop has to do with the voltages, and so here's how you would do a Kirchoff's loop. So if you'd say, all right, this is my Kirchoff's loop that I'm going to do. There's another option for a Kirchoff's loop. So you have to define the loop and define which direction you're going to go through the loop. And I'll give you some examples of that, but this is a pretty good Kirchoff's loop. And then you have to follow the rules for how to do this. So the rules are that if you're going with the current and through a resistor, that means the potential is going to drop. In other words, that there's a certain amount of energy here with this current, but then this resistor is sort of dissipating some of that energy. So the potential, remember, the potential is related to how much energy is going to drop. If for some reason you do the opposite, if you go through a resistor for which the current is going against you, well, then actually the potential is going to increase, because there's more energy on this side than there is on that side, so to speak. More potential energy, in other words. Then if you're going through a battery, if you go this way through a battery from the negative end to the positive end as part of your Kirchoff's loop, well, then the change in voltage is plus the voltage of the battery, which this is like a giant, confusingly, this is a giant E thing, which I don't know why they chose this symbol, but I would just call this V battery myself. But so if you're going this way through a battery, then your voltage increases because it's a battery. The whole point of it is to increase the electric potential, right? But if you're going this way through a battery, your voltage actually drops, because this part is lower potential than this part. So I'll give you some examples of how to do that. Okay, so here's how we do this. So here's our Kirchoff's loop, and you have to pick a part of the Kirchoff's loop to start in. In my opinion, the easiest way, best way to do it is to start so that the first thing is the battery. The first thing you do is go through the battery, because that's always really easy. If you're going this way through the battery, then the first thing in your Kirchoff's loop is plus the voltage of the battery. Can't screw that up. All right. Next one, going up here, going from here to here. Well, from the looks of this circuit, it looks a lot like the current is sort of going this way, right? So the current's sort of coming up out of the battery. In other words, electrons are being sucked towards the positive end thing of this battery, which means the current will be up. So the current should be this way through this resistor. And so if we're going with the current through this resistor, that means that it's a potential drop, so minus I1 R1. Again, even though the current splits here, it's very likely the current is going down here. So as we're going through this loop, we're going with the current. So that's a minus I2 R2. And then again, the current's going this way, we're going with the current, that'll be a minus I4 R4. So so this is what's called a Kirchoff's loop, and the point of this is that if you get back to where you started from, well, then your change in voltage of all this is 0. So that's why that's equal to 0. Because if your voltage changes, and then it changes, and then it changes, and it changes, and it gets back to where you started, well, clearly your voltage is the same as where you started from. So the change in voltage is 0. Okay, so that's one Kirchoff's loop. And I hope that you can see from these equations that you'd come to the same conclusion as, this crazy deal that I was talking about just a moment ago. Okay? But there's another Kirchoff's loop, which is this. And you can do the same song and dance. You can go through the battery. That's the easy part, so that's plus the battery. Again, going with the current, so minus I1 R1. Probably going with the current here, right? It'd be very strange if this current was up and that one was down. That wouldn't make a lot of sense. So you're probably going with the current there. And then this gives you another set of equations, and then you can solve the set of equations, ultimately try to find I1 and I4, which of course is the same as the current in the battery. So that's how you would do it with the Kirchoff's way. Now, the Kirchoff's way, my way, is quite a bit more complicated than, say, the equivalent resistance way, but what you will often be asked are things like, what is the current through R2? What's the current through R3? And in those situations, it's hard not to do this stuff. If all you need is the current through the battery, then yeah, the equivalent resistance should be fine. But often I'm asking you these kinds of questions. So the other reason that the Kirchoff's method is very useful is because we'll sometimes have circuits that have two batteries in them, and so for one, it is literally impossible to use my little Chris Orban way to navigate this circuit, and the reason it's one of the reasons why it's so hard is that it's not clear whether this battery is charging this battery. So instead of current coming out of this battery, you might be putting current into this battery. In other words, like sucking electrons out of it. So instead of sucking electrons into this positive lead and shoving them out the other way, it could be that we're pulling electrons out of this positive lead, thus making it more positive because we're trying to charge a thing. Or maybe both these batteries are discharging, and the whole point of the circuit is to try to push as much current through R3 as possible. And it is not obvious what this circuit is doing without knowing what these voltages are, without knowing what the value of R3 is. If R3 is like super huge, mega ohm or whatever, then maybe we're charging this thing or we're charging that thing. So the Kirchoff's loop method is one of the few things that can help you navigate these types of circuits. So again, here's the rules. Again, the current would be coming out of the battery under normal circumstances, unless it's being charged. In that case, it would be the opposite. I think I just said that. Again, under normal circumstances, but charging is flipped. Now, right. So you might be wondering, you might be staring at me and wondering and say, okay, well, like, Chris, I don't have an ability to stare at the circuit and just intuitively know which direction the current is going to be through, say, R3 or something like that, or R1. Well, the answer to that is that neither do I, but if you guess that the current is going, say, this way through R1, which would imply that battery 2 is discharging, right? If you guess that I1 is this way, I mean, the diagram gives it to you that way, and you find that it's a negative current, well then that's fine. That just means that the current's going the opposite direction that you assumed that it was. So no big deal. So let's break this down. So here's the first Kirchoff's loop that we can do. Again, I always try to be easy on myself, make sure that the first thing we go through is the battery. That's the easy part, so that's going to increase the voltage by the voltage of battery 1. The voltages of these batteries are not necessarily the same. This might be 9 volts, it might be 10 volts, I don't know. And so the first part, going to the battery, that's easy. The diagram encourages us to assume that the current is going this way through R2. And so if we go from here to here, that's going to be a voltage drop. So there's a minus sign there. And then based on these arrows, it seems likely that the current is going this way through R3, and so if we're going through this loop, if we're going through this loop like that, then we're going with the current through R3, and so there'll be another minus sign with R3. So there you go. Now we can do another Kirchoff's loop up here, let's see how we're going to do this one. You can actually go either clockwise or counterclockwise. If you go clockwise, so let's see, if you go clockwise, then you have to do it like this, because if this current is going this way, then you're going against the current here, which means you're increasing your potential. The change of potential here is positive here. And then you're going this way, right? So the current is going like this, but you're going like that, so you're going opposite to the current, so that's a positive. It's a plus sign there. And then you're going not the usual way through the battery, you're going the opposite of the usual way, so you have a minus sign there. For my money, it's a little bit easier to think about this thing if you do it counterclockwise, in which you go through the battery this way, so it's going to be an increase of potential, so plus V battery. The current's going this way, and so it's going to be a potential drop, and then current's going this way, so we're going with the current now with counterclockwise, and so potential drop there. Either way, you get the same equation. Hope that you can see that. But that's what you get. And then there's actually a third Kirchoff's loop that we can do in this circuit, which is going in the outer perimeter, which is an interesting one to do. And if you do that, again, go easy on yourself. Go through this battery first. Go through the battery first, okay? So that's increase of potential. Current's going this way, so potential drop. But then up here, the current is going this way, but we're going this way, and so that's a potential increase. And then because we're going like not the usual way through the battery, then that's going to be a potential drop there. And so you end up with this equation, and then if you do it counterclockwise, you get the opposite of that, but the two are equivalent. So this is actually probably maybe the most interesting equation here, because it talks about the potential difference in the battery. They're directly compared. So again, we have these equations, we have the earlier equations from Kirchoff's loop, this junction has to be true, and we just sort of put those all together and try to solve for whatever it is that the question is asking for. Maybe it's I3, maybe it's I1, maybe it's I2, those sorts of things. Okay, other rules to consider. It's possible that there are circuits in which two wires cross like this, and you might have two currents coming in and two currents going out, in which case you might want to write down this. So that's something to bear in mind. Again, yes, you might see something like that. Something that electrical engineers do that I find to be annoying, personally, is to do something like this, in which you assume that the currents are all going towards the center, and then you later on you find out that one of these is actually negative, and in which case that current would be going the opposite way. So there was actually a physics TA that he used to teach with me at Marion, and this was his preferred way of doing circuit problems, because if you take electrical engineering courses, apparently this is what they strongly reinforce. So that's fine. It's not how I would do it, but it's it's equivalent to expecting one of these to be negative is fine, as long as you're expecting it. You might find that one of these is negative, right? You might say, well, I think current's going to be coming in like this and going out like this, but maybe one of these is wrong. Maybe So this way is, I don't know, anticipating that you might be wrong. I don't know. It's not a bad plan to do it. It's not how I would do it, but it works. All right. So now let's talk about circuits in which they have both resistors and capacitors. So thus far, I don't think we've really done anything with both resistors and capacitors. I apologize if these resistors don't look great, but So we've got a battery here. This is a battery, this is a capacitor, this is a resistor. What happens at t equals 0 when you complete the circuit? And do you get a current or not? Is an important question to ask. Well, here's a question. So how much charge is on the capacitor in this first split-second moment after we connect the switch? How much charge is on that capacitor? The answer is essentially that if it really is that first split-second moment, then there just hasn't had time enough for these capacitor walls to get charged up. Initially, there's zero charge here and there's zero charge here. In spite of the fact that the battery is connected like this, the battery doesn't really do anything unless there's like a closed circuit, right? So the charge on this plate and the charge on this plate are both zero. That's also true in the split second after you connect the thing. Over time it can change, but again at the very first moment it's zero. And so so that's important because the voltage drop across the capacitor, remember Q equals C delta V? Well, if Q is 0, then the voltage drop is going to be 0. And so you can think of this circuit as, so the voltage drop is 0. Another way of thinking about that is if the electric field inside of it is 0, the voltage drop is 0. So again, we find that the voltage drop across this part of the thing is 0. And so it sounds crazy, but the equivalent circuit at that initial moment would look like this. Now I say it sounds crazy because, physically there's no real connection between this wire and that wire, right? Physically that's not actually connected. There's no physical way for charges to move across the thing. But you can still have currents if the capacitor is charging up. So again, charge is not actually crossing it, but as long as it's charging up, you can still have a current. And the current, in this case, again, at this initial moment, would be given by the voltage of the battery divided by the resistance of the resistor. I think I just said that this is charging up. So the idea here is that you can have a current because what's happening is that you're sucking the electrons off of this plate. And so if the electrons are going this way, then the current is going, towards me. And over here, if you are shoving electrons onto the negative plate, electrons going this way gives you a current that's going this way. So no matter which way you think about it, the current would be going like this. It's kind of weird, but that is what happens. So if you think about the voltages in the circuit let's say over a longer period of time, so we've got the voltage of the battery, and then there's a potential drop across the capacitor and a potential drop across the resistor. You're going to find that this is true. And so initially the voltage across the capacitor is 0, and the voltage across the resistor is equal to the battery, which is how we find the current. But over time, as the capacitor charges up, there's going to be less and less current through the resistor, and eventually the voltage across the resistor will be 0. So this is what we expect for how the voltage relates to the charge and the current and those sorts of things. So if you wanted to solve for the current, it might look like this. And so eventually when Q over C equals the battery, then the current indeed is 0. So, so eventually this gets charged up, and then eventually this gets charged up. This circuit, interestingly, is a lot like a defibrillator. In a defibrillator, you might not intentionally have a resistor here to try to that might slow it down for charging up, but there might be some natural resistance in the wires that are connected to the capacitor. And so you charge it up. Eventually, when it's charged up, there's no current, and then you can discharge. You can disconnect the thing and then use this capacitor as sort of like a super battery to give like a nice electric shock. I really like to keep reinforcing this because there's questions on the next midterm that will do it. So if the electric fields, what is that? It's me to update my computer. Not excited about that. So if you have electric fields like this in a resistor, as we talked about, the electrons would go the opposite way, because the electric fields are the direction of the force on a positive charge, which is the opposite of the direction of the force on a negative charge. So the electrons would sort of go this way, like that. But remember, the electrons are going this way, then the current is going this way. So the current tends to go in the same direction as the electric fields, which is interesting. So something like this happens. All right. I think I said all these things already. Already showed these equations. Yep. Okay, here's another circuit that we could talk about. So instead of having the capacitor in series with the resistor and the battery, now the capacitor is kind of separate, and you can flip this switch and charge up the capacitor, and then flip the switch over here, and then discharge the capacitor. So when this switch is flipped over here, now we're charging this thing up. By the way, this is very similar to what's in the programming lab, so programming lab 4. You're going to charge up this capacitor, and the battery is going to suck a bunch of negative charges from here, leaving it positive, and it's going to shove a bunch of negative charges here, making it negative. So this capacitor gets charged up, and then a moment later we can flip the switch back again. It doesn't even really need to be that fast, honestly, because the capacitor will hold its charge until we connect it to something else. But let's say we flip the switch, and then now this is acting like a battery, and the battery is no longer completing a circuit, so it's almost like the battery's not there. And so now this capacitor acts as a kind of a battery, but it's not a very good battery because the voltage decreases over time because the voltage is Q over C. And so we can analyze how quickly that charge is depleted. And this is also related to, again, related to the programming lab. So the first thing to think about in terms of analyzing this discharge is to realize that the battery really doesn't matter if it's not making a completed circuit, and it's literally like the battery's not there. So that's step one. The other thing to realize is that the potential drop across the capacitor should be the same as the potential drop across the resistor. So again, thinking of this as like a battery, so you come to this conclusion, right? And then remember that Q equals CV, which means that V equals Q over C, and the voltage drop across the resistor is just IR. And so you end up with something like this. Okay. So from here you have some options on how to proceed with solving what happens to the charge that's on the capacitor. In other words, as these electrons repel each other and move through the circuit to neutralize the positive charge there, you can either think about this problem with calculus, which is what we're going to do on the next slide, or you can use a computer to do it, which is what the RC Circuit Programming Lab does. So there's this is a sort of HTML backup for the RC Circuit Programming Lab, but basically there's some code here that is going to run over and over and over and over again, and every time that it runs, it's going to check what's the voltage across the capacitor. It's going to use that to figure out how much current is there. It's going to use that current to figure out how much charge leaves the capacitor in this tiny little bit of time, dt, delta t. And then based on how much charge leaves the thing, the remaining charge, we use that to calculate how much voltage is left on the capacitor, and then we use that voltage on the capacitor to calculate what the current is again. We do this over and over and over again. Computers are very good at doing these types of things. So that's one way to approach the problem, which you're going to do on the RC Circuit Programming Lab. The other way to do it is with calculus. This is what we'll do on the next slide. So we're going to take this equation, right, using the current is the amount of charge moving over some interval of time. And so we're going to take that equation, and we can rearrange it a little bit. So we can multiply both sides by delta t and divide both sides by r to get something like this. And now let's imagine that it's some very, very short interval of time. Some would even say infinitesimal period of time. And then this equation turns into that. And now we're actually going to integrate it. And when we integrate it, the left side of this thing is quite a bit easier than the right side, because r and c are both constants, and so they're not changing with time. So the only time dependence here is dt, and so the left side of this thing is just going to integrate to t, right? So this thing is just going to integrate to t over rc, or minus t over rc. The right side of this thing is a little bit more interesting. So this looks a lot like dx, the integral of dx over x. So does anybody recognize that one? It's natural log is what it is. And so this ends up being equal to that. Like I said, the left side is relatively simple. And then we also have to think about the limits here. So there's, right now, the charge is, at time t, the charge is q, but originally the charge is q0. What we really want to do is we really want to figure out what this charge as a function of time is, and so that's what we're really trying to solve for. And a trick that we can use to do that is that we really kind of want to get rid of this natural log. And so to do that, the trick is to exponentiate both sides. So if you exponentiate the left side and the right side, the exponential of a log is just the thing itself. And that ultimately can show, from this you can show that this is true. And so when t equals 0, you get e to the 0. E to the 0 is 1, right? So when t equals 0, you get q0 here. And when t is very large, let's say t is infinite, well, e to the minus infinity is 0, right? So as after a long time passes, the charge on the capacitor is going to be 0, which makes a lot of sense, right? Now, one thing that we like to do with this equation is we like to say that this RC thing, we'd like to rewrite it as minus t over tau, which is a kind of, we call that a time constant. And in this case, the time constant is RC. And the idea there is that if we were just watching this thing discharge and we didn't already know what the capacitance and the resistance was, the only thing that we actually can measure from that would be this time t. So for example, my laptop power cable, when it's connected to the wall, has this little light on it to show that it's connected. But when I disconnect it from the wall, that light stays on for a little bit, but eventually goes down to 0. So I can disconnect that. So this is my laptop power cable. It's not connected to anything else now. Hopefully you can see. And if you look at the power cable, the light is still there. It's not quite as bright. You can still kind of see it. And now it is almost gone. And yep, it's totally gone now. So this thing, whatever it's doing, when you disconnected it from the power source, there's still energy on the capacitors inside of this thing. There's tiny little capacitors. And once you disconnect it, it can still discharge, but it takes a certain amount of time, and the time it takes is not how quickly the electrons can move. Electrons can move very, very fast. But the time it takes is related to the resistance and the capacitance, which could add up to something like 30 seconds or so from the time when I unplug this thing to the time where the light goes away. So I believe this phenomena is related both to this. It's also related to wireless routers. So if maybe you've been thinking about wireless routers more with all this distance learning. When you need to reset a wireless router, it tells you to press the reset button for something like 30 seconds. Now, electrons move very fast. You shouldn't need to wait 30 seconds for those electrons to move, but the thing that dominates the process is the resistance of that device and the capacitance of the capacitors inside of that device. And so on your wireless router, it stores information in tiny little capacitors. And so to make sure all those capacitors discharge, you need to make sure to press that reset button for much longer than whatever the resistance times the capacitance is, so that the charge in those capacitors can all dissipate away. So I believe that's connected to this discussion as well. So there's some extra slides here that I'm not going to go over that has to do with not discharging capacitors but charging them up. And so I wanted to give you some advice if you're interested on how you would treat that. But that's about all I had for today, so I hope this is helpful for the homework and the programming lab and various other things in the worksheet. So, all right, till next time.